Welcome to Brain Vision.
Assuming that the center of mass does not move, we have for the two particles that the total momentum will be zero. So the two particles will either be approaching each other, moving away from each other, or will both be at rest, if only momentarily. So u1 is the velocity of one particle, and u2 is the velocity of the other particle, and m1 and m2 are their masses. So we then have that from this relation, we can obtain one velocity in terms of the other. For example, u2 will equal negative m1 over m2 times u1. Or the magnitude of u2 simply equals m1 over m2 times the magnitude of u1. The total velocity will then be the magnitudes, really the speed, the total speed, will be the magnitudes added together. And when you substitute in the magnitude of u2 in terms of the magnitude of u1, you get the following relation solely in terms of the magnitude u1, which can be rewritten in the following way. So now you can rewrite that, and now we see that u is equal to the sum of the masses divided by m2 times the magnitude of u1. That can be then multiplied and rewritten so that the magnitude u1 is written as mass 2 times u divided by the sum of the masses. Also, we have some more relations we can obtain. So, for example, from the total momentum equaling 0, we have that we can work the other way. We get that the total speed can be rewritten in terms of the magnitude of velocity u2 as well, instead of being rewritten in terms of the magnitude of velocity u1. And this is analogous to how it was rewritten in terms of u1. So this time, u will be written as the sum of the masses divided by m1 instead of being divided by m2 times the magnitude of u2. And then the speed for u2 would be equal to m1 times the speed u divided by the total of the masses, the sum of the masses. So we can use these two relations, these two equations or expressions for the speeds u1 and u2 to get an equation for the kinetic energy and rewrite it. So we substitute them into the squares of u1 and u2 in the kinetic energy. And the result that we get is the following. So we see in this first step, we substitute looking at the expressions for u1 and u2. And what we have is m2 and m1 squared in the numerator, as well as u squared. And then we have the sum of the masses squared in the denominator. And of course, the potential term is unaffected. It only depends on x squared, and x is the relative position between the two particles. So continuing with this, we'll be able to do some factoring between these two terms in the kinetic energy. And this is the proper way to factor here. And I meant to write the potential energy over here, but this won't affect the factoring that we're doing in the kinetic energy, but that should be written there properly there so that we have, well, actually it was written there, but that's okay. Okay, so now we have it. So now you can pull factors out that these two terms have in common, and you get this that results. And you see that m1 plus m2 in the numerator will cancel with m1 plus m2 in the denominator. And this is what we have. So comparing one more time with the last line, we have the reduced mass m1 times m2 divided by m1 plus m2, multiplying the magnitude of the relative velocity. And again, the potential energy is expressed in terms of the relative position. So we can simply write mu for m1 times m2 over m1 plus m2. So continuing, we also would like to take a derivative of our energy equation and see what we can get from that. So we have our two terms. And of course, since the energy is conserved, it's a constant. We can take the derivative of the entire equation, and that derivative will equal 0. And when doing that, the kinetic energy will look as follows for its derivative, as will the potential energy that we see in this first line after the arrow. But notice that u is actually a derivative itself. It's the first derivative of position x. And so it's the derivative with time of position. And of course, du dx is already a derivative with respect to x. So we have the chain rule going on, dx with respect to time and du with respect to x. So what we've really got here is du with respect to time, du dt, because we're multiplying these two derivatives together by the chain rule from calculus. And in the potential term, we simply get kx. We took the derivative of x squared, and the derivative of a quadratic is 2 times x if you're taking the derivative with respect to x. And again, these two terms add to 0, and the dx's go away in the chain rule, and we have du over dt. So now we have the derivative with respect to time of a speed or a velocity, and that gives us an acceleration. That means that we have a second order equation of motion. So we do have a harmonic. In this case, since we're dealing with a harmonic oscillator, we do have the equation of motion for a harmonic oscillator. And we can write it in this way by bringing the potential term to the right. And that is the Hooke's force equation on the right-hand side. So for this, we can also write it as negative omega squared x, where omega is a typical angular frequency. And recall that an angular frequency can be written as omega equals 2 pi f, f being your linear frequency. So with that in mind, we then have for the frequency of our harmonic oscillator this expression right here. So that is our last and final result there.